Okay, in the previous video we talked about the variance of a random variable, and in this video we're going to talk about the covariance of two random variables. So suppose that you have two random variables, x and y, then we define the covariance of x and y to be the expectation of x minus the expectation of x times y minus the expectation of y. So in other words, what we do is we take x and y, which might have means zero or non-zero, we subtract the means, and then we get these two new random variables. So like, let's call this u and let's call this v. So these are normalized as mean zero, and then we take the expectation of the product. Okay, and notice that if you have the variance of x, that's the expectation of x minus the expectation of x squared. So I guess we don't need that second parenthesis. And this is precisely the covariance of x and x. Okay. And just like for the variance, we can rewrite the covariance of x and y just by distributing. So the covariance of x and y is the expectation of xy minus x times the expectation of y minus the expectation of x times y minus the expectation of x times the expectation of y. And let's just read this to make sure we understand what's going on. So the expectation of y is a number, right? The expectation of x is a number. So you have xy minus a number times x minus a number times y minus a number. And this is going to equal, by the linearity of expectation, the expectation of xy minus the expectation of x times the expectation of y minus the expectation of x times the expectation of y. Oh, sorry, there's a plus here. And then plus the expectation of x times the expectation of y. So this is equal to the expectation of xy minus the expectation of x times the expectation of y. That's another form of writing the covariance. Okay. But here's the original definition. Now, using the covariance, we can calculate the variance of a sum of two random variables. So the theorem is that suppose that you have x1 through xn random variables. Then the variance of the sum of xi's is equal to the sum of the variance of the individual xi's, that these go from I equals 1 to n, plus 2 times the sum of the covariance of xi with xj, where I is strictly less than j. So I goes from 1 to n and j goes from 1 to n, but you have this restriction that I is strictly less than j. So in this sum, we have the covariance of x1 and x2, but not x2 and x1. Actually, those are accounted for, but they're the same. So the covariance of x1 and x2 is the same as the covariance of x2 and x1. And we can make the sum range over the terms where I is less than j because of this 2 in the expression, Right? We have this 2 here. Oops. Okay. So that's the theorem. So how do we prove this? Well, let's introduce some notation. Let mu I be the expectation of xi. Then we know by the linearity of expectation that the expectation of the sum is equal to the sum of the expectations. So it's just the sum of the mu i's. I wonder if I can move this. The sum of the mu i's So what can we say about the variance of the sum? Well, by definition, this is the expectation of, so let's just call this y just to make this easier. So this is the expectation of y minus the expectation of y squared. That's the definition of the variance. So it's the expectation of y minus the sum of the mu I squared, right? Because of this. This is, in terms of our notation, we're saying that the expectation of y is the sum of the mu i's. Okay. And this is the expectation of the sum of the xi's minus the sum of the mu i's squared. And so the sums in the middle are just sums from I equals 1 to n, so it's the expectation of the sum of xi minus mu I squared. And note that when you have a sum of ai's from I equals 1 to n and you square it, so this is a1 plus dot 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 plus an and then squared, this can be rewritten as the sum from I equals 1 to n, sum j equals 1 to n, ai, aj. So why is this true? Okay, let's just look at an example just to explain. So for instance, if we have a1 plus a2 plus a3 in parentheses squared, so this is when n is 3, then this is going to be a1 times a1 plus a1 times a2 plus a1 times a3 plus a2 times a1 plus a2 times a2 plus a2 times a3 plus a3 times a1 plus a3 times a2 plus a3 times a3 times a3. So what you're doing is you're taking the sum of the aij's from j equals 1 to 3 and from I equals 1 to 3. Right? Because what this is, that is the sum from I equals 1 to 3. Sorry, this is aiaj. Oops. aiaj. Because what this double sum is the sum from I equals 1 to 3 of ai a1 plus ai a2 plus ai a3. And so this is just the sum of the 3 rows. Right? This first row is when I equals 1, the second row is when I equals 2, and the third row is when I equals 3. So this is the outside sum when I equals 1, that's when I equals 2, that's when I equals 3. Okay? So that explains this formula here. And we can use that because this sum, see what's happening when I'm taking the sum? I have a1 plus a2 plus a3 and then I also have these other guys. So I have a1 a2 plus a2 a1. Well, a2 a1 is equal to a1 a2. And similarly, I have an a1 a3, and that's the same as a3 a1. And let me pick one more color. If I have A2, A3, that's the same as A3, A2. So what I have is the sum of the AI squared. So I have the blue terms, so AI squared from I equals 1 to n. But then I'm also adding 2 times the sum of the AI AJ, where I is strictly less than j. Because I have the terms where I is strictly less than j is I have this one, and that one, and that one. So I am adding these, but then I have to multiply by 2 because I have the ones below the diagonal. Right? I have the A2, A1, A3, A1, A3, A2. So that's where I get this formula. And just to be clear, I and j go from 1 to n, but you're only counting the ones where I is strictly less than j, but that's accounted for by the 2. Okay, now how do we use this? Well, we have the sum. So the sum from I equals 1 to n of xi minus mu I squared is going to equal, so we're using ai as xi minus mu I, right? So if you plug it into the formula, you get the sum of xi oh, sorry, this is, I am squaring the whole thing. I'm squaring this, right? So this is what I get when I have that, and then if you use the formula we found, this is going to be the sum from I equals 1 to n of xi minus mu I squared plus 2 times the sum I less than or equal to I less than j less than or equal to n of xi minus mu I xj minus mu j. That's literally just from taking what we get with the AIs equal to xi minus mu I. So therefore, by the linearity of expectation, the expectation of this guy, the expectation of the sum from I equals 1 to n of xi minus mu I squared, so this whole thing squared and then the expectation of that is equal to, so I have the expectation of this term and then the expectation of that term, but each of those terms are sums, so I apply the linearity to each of those, so I get the sum from I equals 1 to n, the expectation of xi minus mu I squared, plus 2 times the sum of the expectation of xi minus mu I times xj minus mu j. And this is precisely, this term here is the sum of the variances of the xi. And then each of these terms is the covariance of xi and xj. And so we get the formula. We get the sum of the variances of the xi's from 1 to n plus 2 times the sum of the covariance of xi and xj, where I is strictly less than j. So that's the proof. So not very complicated, actually, right? You're just using the linearity of the expectation over and over and over. I mean, we just have this little thing where you had the square of a sum, and then we just wrote out what that was. So it's basically, you have the square of a sum of random variables, and then you just write it all out, and then apply the expectation to each of those, and then add them up. Okay. So this formula leads us to the next definition, which says that random variables, so we say that random variables x1 through xn are uncorrelated if whenever I is not equal to j, the covariance of xi and xj is 0. And later we'll talk about the correlation of random variables and see that the uncorrelated random variables have covariance equal to 0. So in this case, we've seen that the variance of the sum is equal to the sum of the individual variances. That's if you have uncorrelated random variables. Also, independent random variables are uncorrelated. Okay, why is that true? Well, recall that the covariance, we found that the covariance of x times, the covariance of x and y is equal to the expectation of xy minus the expectation of x times the expectation of y. So if this guy is 0, then we get that the expectation of xy is equal to the expectation of x times the expectation of y. So we have, if the covariance of xi and xj are all 0, then we get that the expectation of xi xj is equal to the expectation of xi times the expectation of xj. And hold on, I'm working backwards. Independent random variables are uncorrelated, right? So if you have two independent random variables, okay, then you have that the expectation of xi xj equals expectation of xi times the expectation of xj, and that implies that the covariance is 0. So let's just write this down. So independent implies that, so this is a property of expectation. If x and y are independent, then the expectation of xy is equal to the expectation of x times the expectation of y. So if you have pairwise independent random variables, then we get that the expectation of xi xj is equal to the expectation of xi times the expectation of xj, and then that implies that the covariance of xi and xj is equal to 0. Okay. Now we know that if you have uncorrelated random variables, then the sum of the variances is equal to the variance of the sum. But it's not true that whenever you have two random variables, then the variance of the sum is the sum of the variances. Because you could have two, so let's give an example of two random variables that are correlated. So suppose that x is a random variable with a non-zero variance, okay, finite, and consider x1 to be x and x2 to be negative x. Well, the variance of x1 plus x2, so x1 plus x2 is just the 0 function, so the variance is 0, but the variance of x1 plus the variance of x2 is equal to 2 times the variance of x. And if the variance of x is not 0, which we assume, then they are not the same. So in general, they're not equal. Another example, again, letting x be a random variable with a finite variance, non-zero variance, we can take x1 to be x and x2 to be x. Then the variance of x1 plus x2 is just the variance of 2x, which we know is 4 times the variance of x. But the variance of x1 plus the variance of x2 is equal to 2 times the variance of x. So these are also not equal. So x and x are uncorrelated, they are correlated random variables. Okay. And let's just use these facts to give an example, an application of the fact that when you have independent random variables, then the sum of the variances is the variance of the sum. Let's use that to find the variance of the binomial distribution. Because recall that the binomial distribution comes from a sum of independent trials. So let's find first the Bernoulli distribution, the variance of the Bernoulli distribution. So remember, that's when the random variable x is equal to 1 with probability p and 0 with probability 1 minus p for some p between 0 and 1. Then the expectation of x is equal to p times 1 plus 1 minus p times 0, and that's p. Well, what about the expectation of x squared? The expectation of x squared, well, x squared, so what is the function x squared? I mean, that's going to be 1 if x is 1 and 0 if x is 0. So x squared is equal to 1 with probability p and 0 with probability 1 minus p. And so the expectation of x squared is just the same as the expectation of x, which is p. So therefore, the variance of x is going to equal the expectation of x squared minus the square of the expectation, right? That's the formula. And then this is p minus p squared, which we can write as p times 1 minus p. Okay, so now let's apply this to the binomial distribution. So suppose that we have a sequence of independent trials with success probability p, and let xi be 1 if the ith trial is a success, and 0 otherwise. So we count the total number of successes Sn in the first n trials. Well, that's just going to be x1 plus ... plus xn. And this has a binomial distribution with parameters n and p. So the variance, since the xi's are independent, the variance of Sn is the sum of the individual variances, but the variance of xi is just p times 1 minus p, and you have n of these, so it's going to be np times 1 minus p. And that's just an application of what we have proved before. We're going to use the covariance to define the correlation of two random variables. And basically, if the covariance is positive, so in general, what is the meaning of the sign of the covariance if the covariance of x1 and x2 is positive, then what it means is if x1 is large, then x2 is more likely to be large. So, for instance, you can have x1 be the height and x2 be the weight. So x1 is the height of a person, x2 is the person's weight. Or x1 is the score on the first midterm, first exam, and then x2 would be the score on the second exam. Basically, when we have a positive covariance, the two random variables are correlated positively. And if you have a negative correlation or negative covariance, then one way to interpret that is if x1 is large, then x2 is less likely to be large. Basically, if x1 increases, then x2 is expected to decrease. So, if salary is correlated with years of education, then x1 might be the number of years of school completed, and then x2 might be the number of dollars earned per year. Okay, and we'll talk more about correlation next time.